All right, welcome students, and once again we're going to deal with structure of the atom, and in this case we're going to specifically deal with element notation and kind of how it can be useful. So we're going to dive right in um, here with that. First thing, we want to identify a couple things, and one is the atomic number, which you should be familiar with, and the definition for that basically is going to be it's the amount of protons in the nucleus. Okay, that's what it is, the atomic number. A lot of times it's abbreviation, as you'll notice here, is Z. So if you see in your review questions or in the book, it refers to Z and then it gives a number. It's the atomic number that it's referring to, or the number of protons. Something that you may want to note that is important is, what do the protons do? Protons determine the identity of an element. So that is something important to make sure that is written down if you don't already have that written down in your notes. So that's what atomic number is, and that's what it keeps track of. And generally speaking, in what we would call a normal atom, protons and electrons are equal because most atoms are neutral. So if you know the protons, then you also know the electrons. So that's kind of why it's useful to know the atomic number. Now, along with that is this concept we call isotopes. And I had some of you guys ask me in class dealing with, what about neutrons, or what do they do? How do they play a role, or what's atomic mass? I think in one of the classes I even posed, well, if you look at your atomic or your periodic table and you notice the atomic weight there, that it's often in decimal form. Why is that? Especially if we consider that the mass of a proton and mass of a neutron is 1. Why do we end up with these weird decimal numbers? Okay, well, there's a couple reasons. One is isotopes. Okay, what is an isotope? It's an element that can have different numbers of neutrons. And so it's the same element. In other words, it has the same atomic number, same number of protons, but different numbers of neutrons. A great example of this would be, a lot of you guys have heard of carbon-14 or carbon-14 dating. Well, normal carbon that makes up most of your body is what we call carbon-12. That's the stable, non-radioactive form of carbon. However, there is a small amount of carbon-14, and what carbon-14 is that is the isotope. In this case, it's a radioactive isotope of normal carbon. And so to understand what is an isotope, well, they're both carbon, so they have the same number of protons. Remember, protons can't change. They determine the identity. So in carbon, I will always have 6 protons no matter what. That will never, ever change. The only thing that can change are neutrons and electrons. And when it comes to dealing with mass, it's neutrons that change. So I can have carbon-12 and I can have carbon-14. Well, what's the difference? The difference is the number of neutrons. And really those two numbers, carbon-12 and carbon-14, are the masses, okay, what we call the atomic mass number. So what is the atomic mass number? A, which represents the atomic mass number, equals Z, which is your number of protons. Remember, that's your atomic number, plus your number of neutrons. Okay, so basically, as long as I know how many protons I have and how many neutrons I have, I'm going to simply add those together, and that gives me my mass number. So that's where you come up with carbon-12 is your most common type of carbon, and so that would tell you, carbon's atomic number is 6, and if its mass number is 12, well then it must have 6 neutrons, because 6 and 6 make 12. Now carbon-14 though, well, I know it's still carbon, so what has to be the same? That's right, it's the number of protons. Okay, protons have to be the same. So that can't change, but what can change? Well, the neutrons can change. So if it's now carbon-14, then instead of having 6 neutrons, I now have how many? That's right, 8. So 6 and 8 equal 14. So that's what an isotope is. It's the same element, but it has a different mass because my number of neutrons have changed. And that change in mass can affect what goes on in the nucleus, and we're not really at nuclear chemistry yet. So I'm not going to go into a lot of detail there, but that's what we call an isotope. That's the basic idea behind it. Now, how do we write or designate something as an isotope? Well, that's where, if you look in your notes, you have something called isotopic notation. So we're going to take a look at that. what isotopic notation is. And here's an example of some isotopic notation. And you're going to have to know how to write this. So for example, you might be told that oxygen here. Well, the first thing you're going to do in isotopic notation is you're going to write the symbol itself. So like you have oxygen there, you're going to write an O. And then the second thing you're going to do is you're going to write the atomic number, which you will know. If it's oxygen, you'll know what the atomic number is. It's 8. It's right there on the periodic table. And that always goes in the bottom left. Okay, if you notice right there with oxygen, I've got an 8. That's the atomic number. So in your notes, you may want to designate what that 8 is, okay, and where it goes. That is important because every year I get students who mix these up and they put things in the wrong spot. So what does that 8 tell me? That tells me that's the number of protons. Hey, what about that 16? What's that 16? Okay, well, that's the atomic number. Okay, well, what's the atomic mass number? The atomic mass number is the number of protons and neutrons together. Okay, so that 16 is not just neutrons, it's neutrons and protons together. So now from this, I should be able to find some key pieces of information. And so, for example, on the test, and I think we do this in your review questions as well, I can give you some isotopic notation. And from this, you should be able to tell me, number one, how many protons does it have? Where would you look for that? I would look for my atomic number, which is in the bottom left. Okay, so that I know I have 8 protons. And I should also be able to figure out number of neutrons. Well, how can I figure out neutrons? Well, I know my atomic mass number, which is the top left number there, is 16, and that's protons and neutrons together. I know my protons is 8, so if I subtract those two, then I'm left with just neutrons. So 16 minus 8 gives me my number of neutrons, which happens to be in this case 8 as well. That's not always the case. So now I know my protons and my neutrons. What about electrons? Do I know electrons? Well, if it's a normal atom, okay, by normal atom we mean one that does not have a charge, and neither of these has a charge written there, then I know that my protons and my electrons are the same. They have the same amount. And so I have 8 protons, and therefore I have 8 electrons. So a question I might ask you on the test, hint, hint, by the way, would be something along the lines of, okay, in this here, if I gave you this isotopic notation, tell me how many protons, neutrons, and electrons it has. So I want you to do that for the next one here, carbon. I want you to try to figure out how many protons, neutrons, and electrons it has based on the information we just went over. And then we'll do some more practice in class with this. And then I might also ask you to do the reverse. I might tell you, okay, this thing has 7 protons and it has 12 neutrons. Write for me what this substance is in isotopic notation. So you would look at the protons to identify the element, and then you would put the atomic number at the bottom left. You would add the protons and neutrons together to get the atomic number and put that at the bottom or the top left, and then you'd be done. So we're going to do some more practice with that in class. But I wanted you guys to understand that's what isotopic notation is. This is what it looks like here. The symbol with the atomic mass number at the upper left, and the bottom left is the atomic number. All right, continuing on, what else have we got? Okay, the atomic mass, just to kind of let you know, I'm going to put all this up here so you can kind of copy it down as we go on. The atomic mass is based off of 1/12 of a carbon atom. Why a carbon atom? Because generally speaking, a carbon atom has 6 protons and 6 neutrons, and its mass is basically 12, so we define it as 1/12 of that. We call it an AMU. Why do we use, that's the unit for measuring mass when dealing with atoms, simply because you can't measure it in grams because it's so incredibly tiny. You would get like 0.00000000000, way out there, and it would be meaningless to us. So we use a different unit called an AMU. Now we're actually not going to deal with this a whole lot in class, but that's just kind of nice information to know. and basically that mass is the same as a proton or a neutron, and they're roughly speaking about the same. I think the neutron is slightly heavier than the proton. It's like 0.0001 heavier than the proton, but that's not relevant to what we're dealing with. Valence electrons. We're finally here. I know I've mentioned them several times, and that this is going to be kind of important, and it is going to be super important in the upcoming chapters that we understand what valence electrons are, and we are finally here at this point. So let's define them. Valence electrons are the electrons in the outermost energy level. Super important that you understand what we're saying here. Here's the key word. If I was to highlight this, this is the word that I would circle. Okay, outermost energy level. Okay, this right here is what's important. Okay, not sublevel, but outermost energy level. That's what's key in this here. So make sure that we understand that as we're going through, that this is not anything else, no sublevels or anything like that are involved here. And we need to advance, and it's not advancing. There we go. Okay. They occupy the highest numbered S and P sublevels. Okay, so we're only dealing with S and P sublevels. We're not dealing with any Ds or Fs. So the maximum valence electrons that you can have is 8, because S can hold 2, P can hold 6. So the maximum electrons I can have for valence electrons are 8. I should never end up with 10 or 12 or 20 valence electrons. I can only end up with 8. So keep that in your mind. That's super important. Now, how do I go about writing valence electrons? Well, we use what's called electron dot notation. And there's a couple rules that kind of are important. And what we use are dots, and really you can use any symbol, but use dots are the easiest because they're the fastest to write. Valence electrons. And there's a maximum of 8 dots because, as we just got done saying, there's a maximum of 8 valence electrons. You can't have any more. So what are the rules for placing dots? Well, the first rule is the first 2 dots go on the same side. So what you're going to do is you're going to write the symbol of the element, whatever that may be. We're going to use oxygen here in just a minute. And the first 2 dots go on the same side. So if you have 2 electrons to place, then the first 2 dots go on the same side because that side represents the s orbital. Remember, there's only one orbital in the s sublevel, so we're going to put them both there. Then, if you have any other electrons, then they would go in the p sublevel. And remember, the p has 3 orbitals, so those are the other 3 sides to the, if you had the symbol, you would have 4 sides, top, bottom, left, right. And so I've filled in one side already, the s orbital. If I have more electrons, then I'm going to put 1 in each of those 3 sides before I fill a side. Just like we did with the arrows and the orbital notation, I have to put 1 dot on each before I can fill a side. So let's kind of see how this works. Here's my oxygen. Oxygen has 6 valence electrons. That's kind of a freebie. So what am I going to do with those 6 valence electrons? Well, first, I'm going to put my first dot and my second dot together on the same side because I'm filling my s orbital. Then I'm going to put my next dots, okay, 1 on each side. Okay, so I've got 5 dots taken care of. So top, bottom, left, right here. First 2 dots went together. Then my other dots, these are all called unpaired electrons right now. Now I'm going to put my 6th electron. I can now pair it with something, and you'll notice I have 2 sides that are paired and 2 sides that are what we call unpaired. These are representing my valence electrons. This is what we call electron dot structure. And we will be using this extensively as we go throughout the rest of the year. So we'll do some practice with that in class. Ions, last thing here. We talked about that protons can't change, but neutrons can change, and also electrons. If electrons change, then it isn't isotopes that you get, it's an ion. So what is an ion? Here it is. It's when you lose or gain electrons, and it gives the atom an electrical charge. And you can have one of 2 situations happen. Okay? The first is you can form what's called a cation, which is a positively charged atom, which would be when you lose an electron. Because remember, electrons are negative, so if they move away from the atom, then what will be left? You'll have more positives than you will negatives. The other is, the opposite to that is true, and it's called an anion, which is a negatively charged atom. and that's when you gain electrons. So those are ions, when we gain electrons. All right, we are done.